Now I've already looked at this antenna before. If you look at my back catalogue, you'll this antenna's and its weaknesses described as no improvement to parliamentarians. This is my favourite antenna, this one here on the left. It's a CD28-41-70 series antenna, and I've already described this as my favourite antenna also in a video on my back catalogue, and I've done a tips and tricks video on this antenna as well. What we're going to do today is we're going to have a look at a closer look at this antenna here, and get a better idea of how it's made up, and how you can test it in the field. Now, when you're looking at these two antennas, you'll notice that the antenna on the right is somewhat taller than the one on the left, particularly this portion at the bottom here. And you might ask why that's relevant. It's relevant because the upper whip piece, the whip section at the top, is relatively flexible. So if you strike either of these antennas in the whip section, you won't do much damage at all. However, if you strike them down low, you will damage them. And the antenna on the right here is taller than the one on the left, by about a third. So this antenna on the left is about 30% less likely to be damaged by an impact. What we're going to do now is we're going to dissect one of these and have a closer look inside. Okay, we've got the camera in macro mode now, so we can see what's going on here. There's the lower brass piece that fastens onto the bracket. That's the mounting bracket. It also is in direct contact with the braid part of the coaxial cable. So all of that is effectively all in contact. There's a coil here, some sort of inductor. We can see the upper portion of this antenna here, which is all one piece, all the way up to the point where the grub screw is there, just there where the whip aerial attaches. Running through the middle is the center part of the coaxial cable. So that's the center core. It's still covered by the dielectric, and that's running up the inside, up in here. Now we know that the termination length of this antenna is 70 millimeters. We'll just get a ruler out and measure that. And the one thing that surprises me about these antennas is just how much abuse you can put them through. Okay, here we have a close-up of the top section. As you can see, it's a tube. We can actually see where the top part of the coil is soldered. It looks like it inserts into a hole and then it's soldered on. So that's part of the aerial assembly process. And this upper portion is the portion that forms the capacitor. The lower portion here is a little less obvious. And we can see up inside there, that's where the internal threaded piece gets a hold of the coaxial cable braid. But I'm going to put this in the vise and give this a clobbering with a hammer in a minute, because I want to break this away from this lower portion so we can have a good close look at the inside of this, and we'll get an idea of just how robust this antenna is. For this little exercise, I'm going to wear some safety glasses. I'm going to give this a good solid thump with a hammer. The interesting thing is, it's stripped the thread at the bottom rather than actually break this plastic piece. Another idea, I might just crush this in the vise. If I can get it to break. I guess from a rugged point of view it's a pass. And what we have here is we have a hole, and that's where the centre part of the dielectric is going to pass through there. And just off to one side, if I can get this thing to focus, it's in macro mode at the moment, just off to one side is the end of the coil, and it's soldered into this brass fitting, which is the lower piece. Just to get a better view of what's happening here, I've carved a little bit more of the side of this RFI antenna away, and I've exposed the centre portion of a piece of RG58 coax. Now I haven't measured this to its normal 70mm length. Normally when you're terminating this we would have a portion sticking out which would be 70mm, and I haven't done that. But anyway, what actually occurs here when you terminate one of these antennas, this is the internal threaded portion in the base of the antenna, which grips the braid portion of the coax cable. The centre portion goes right up through the centre, right up through the centre of the coil. I'll just try and turn that so it catches the light, and then goes right up and into this upper portion up in here. Now we might cover this a little bit more, but at high RF frequencies a coil is not a short circuit, it's an open circuit. It's a short circuit at DC, but it's effectively an open circuit at high frequency RF, high frequency AC. Up here in this portion we actually have a capacitor forming. Now a capacitor at DC frequencies is normally an open circuit. However, at high frequency RF, high frequency AC, a capacitor is a short circuit. So what we have effectively here is we have RF leaving the centre portion of the coaxial cable, jumping across a capacitor and making contact with the lower part of this antenna, and we have a coil which effectively keeps all of this above ground, because at high frequency it's effectively an open circuit. Now obviously we have a capacitor and a coil. We also have a rudimentary tuning circuit, and of course the remainder of the tuning is actually done by cutting the length of the whip. We've got a whip up here which we trim to length. We have this upper portion which is hollow, and we have a coil, and then in the lower portion we have the base, which is forms the physical mounting, if you like. That's the bit that gets physically mounted. And the coax cable comes up the centre, comes right up through here. That's the centre piece of it, and carries on down the cable. Obviously the braid portion comes up here and makes contact here. This piece here forms a capacitor. Here we have our inductor, and this portion here, here's our coaxial cable. The outer portion is connected here, and that's how the thing is physically fastened to whatever you're going to bolt it to. So that's what we have electrically. We have our centre coming up here, capacitive coupling into the bottom portion of the whip antenna, and we have an inductor. Now these two components here, those two components there form the matching section. The inductor, as I said before, is a DC short circuit at DC frequencies. At high frequencies it's more of an open circuit. The capacitor at DC is an open circuit, but at high frequencies it becomes a short circuit. Now what's critical about all of this is the length of this portion of center conductor inside this upper portion, and that's why it's critical when you measure the portion of the center part of the coax cable forward of the braid. For this particular aerial it's actually 70 millimeters, and the reason why it's 70 millimeters is this piece here forms a fairly precise capacitor. If you don't get this length right here, then this equivalent electric circuit will be incorrect, because the size of this capacitor will be either larger or smaller, and then this tuning circuit won't work properly. Now, something else from a technician's perspective. When you're working with these antennas and you suspect you have a fault, before you pull out a sweep set or a VSWR meter or anything of that nature, one of the first checks that you can make with this particular antenna is you can actually put your multimeter between there and there. Remember, your multimeter works at DC, so you can actually make sure that this coil is still intact and in place between there and there, because when you get right down to it, there's almost nothing else inside this the body of this antenna that can actually go wrong. If you're measuring your 70 millimeters here correctly, then this amount of capacitance here should be correct, and the only other thing which needs to be checked is to ensure this coil is in place between there and there, and you can do that with an ordinary multimeter on the ohms range. Okay, we're out in the backyard. We've jacked up an aerial test rig here. It simply consists of a piece of PVC pipe duct taped to the washing line, and we have a bracket here. That's my my favourite RFI CD28-41-70 antenna, and we've organised this bracket so that it can be very easily turned over. We can just twist it like this. There we go. It's horizontally polarised. That was vertically polarised, and we can invert it by rolling it right over like this, right the way around. Anyway, what you're looking at there is the screen from an Anritsu Sitemaster, and on the left hand side over here we've got 148 megs, 158 megs in the middle, and over this right hand side we've got 168 megs. So we're actually sweeping this antenna over a fairly broad range, and we've got a VSWR of 1 at the bottom and a VSWR of 2 at the top. Now at the moment the antenna is vertical, and what I'm going to do is I'm going to walk up and describe what I'm doing as I'm doing it, and you should be able to see some changes here, particularly as I touch the antenna with my hands. But the purpose of this demonstration is to demonstrate that the antenna will work exactly the same no matter what orientation it has. Okay, so at the moment it's vertical, and you'll see the changes. I'll put my hand on it. I've got my hand on it now. I'm just tipping it over to horizontal, and taking my hand off of it, moving away, I'll let the pattern redraw, and you will notice that the pattern is exactly the same. And I'll walk up to it again, put my hand on it now, and invert this. It's now vertically polarised, but the entire antenna is inverted. Got my hand off of it now. I'm coming back towards the camera, and we'll let the screen trace redraw again. As you can see, there is actually no difference between an upright antenna and an inverted antenna in terms of its VSWR. So the demonstration I am showing you means that this antenna is a viable antenna to mount in an inverted fashion. There's a caveat, of course. I mentioned it before. You've got to seal the coaxial cable up to stop the water from getting inside of it. Anyway, what I'm going to do now is I've got a piece of metal here. I'm going to approach this antenna with a piece of metal and describe to you as I'm going the distance I'm away from this piece of metal. At the moment the antenna is inverted, and the purpose of this demonstration is to give you an idea of how the antenna VSWR changes when pieces of metal come into proximity with the antenna. Now I'm going to start at about half a metre away, and that's about 750 millimetres, about 3/4 of a metre. You just allow the pattern to draw. Now we'll close up to about half a metre away, and we'll allow the pattern to redraw, and we'll get a little bit closer, about 300. We'll just hold it here for a second and allow the pattern to redraw, and I'll move away. So that's about 300 millimetres as we speak. We'll come away to about half a metre. We'll just hold it there while the pattern redraws. We'll come back to about 3/4 of a metre. Hold it there for a second, and I'll come right away now. Now, it's not a particularly large piece of metal, but you'll see from the pattern that there is obviously an effect. The lesson to be learned here is that whenever you're putting an antenna on a vehicle, it pays to keep the antenna at least half a metre away from adjacent metalwork.